All right, welcome back to Chapter 6. Chapter 6 is the start of trigonometry. Now, usually this is one of people's either most enjoyed or most disliked parts of math, but we'll try to make it as easy as possible. So what we're going to do is we're going to start with something that you dealt with back in grade 11, which were radians. We're going to introduce them, and we'll get out of here. So it says, in grade 10, remember when you dealt with angles, we always worked with degrees. So anywhere from a full circle would be 0 degrees to 360 degrees. In grade 11, we extended what we knew by using this terminal arm. Now, what a terminal arm is, it means if we think of the grid and our principal arm starts right along the x-axis, we can take this arm and rotate it around the grid, kind of like a clock working in counterclockwise direction. And what we do is we calculate the angle created between that principal arm that we start with and a terminal arm, which is where it would end. So in a case like this, we'd be calculating the angle between the blue arrow and the red angle. The blue is the principal arm and the red arrow is the terminating arm. So we calculate the angle there. So second one, notice how we go around 210 degrees. So it'd be 90, 180, a little bit more, 210. It's going in this direction. For the next two, they're going the opposite direction. So what they have is a negative angle, negative degree. So negative 45 degrees would be moving clockwise. Negative 210 degrees is also moving clockwise from that principal arm right along the x-axis, 210 degrees around. Remember that each quadrant is 90 degrees. So we're going 90, 180, then 30 more than that, 210, all negative because it's going in the clockwise direction. Then what we did was we got to deal with situations where we said, well, what happens if it goes around more than once? So if our terminal arm went around more than once, we called coterminal angles. So let's have a look at some of these. In this case, 540 degrees. Well, we can think of that as being the arm going around once. That'd be 360 degrees. Plus another 180. So 360 degrees plus 180, that's where we get that 540 from. Continue to the second one, same idea. Well, going around once would be 360 degrees. And then going up to the terminal angle is 45 degrees. And when we add those ones together, that's where we get that 405. So 405 degrees and 45 degrees have the same terminal arm. They're on the same spot, right? It's like a clock. When a clock continues around to, 2:30 or 3:30, well, that minute hand is in the exact same spot. So both are referring to 30 minutes. And same for the last one. Notice this one's going in a negative direction because it's negative 360. So it's going all the way around negative 360, 90, 180, 270. Those two, when we add them together, that's where we get that negative 360 degrees. So it's gone around more than once. And those are called coterminal angles. So let's take this idea and we'll apply it to some other situations. Next one says, recall that the related acute angle, so that's going to be an important one to us. Usually we use this alpha in order to denote that. And for an angle in standard position, it's the acute angle that's created between the terminal arm and always the x-axis, not the y-axis, the x-axis every single time. So let's look at these. The examples that we have below, it says, for each angle, draw the diagram of the angle in standard position and find the related acute angle. So if I'm looking at 150 degrees, well, the principal arm is right along the x-axis here. And what we're going to do is we're going to go up 90, 180. Well, that's too much. Remember, it's increasing by 90 every quadrant. So it must be in the second quadrant here. Something like this. This is 150 degrees. Our related acute angle is the angle that's created between the x-axis and the terminal arm every single time. So what is our alpha value? Well, if it's 180 degrees here, and I've used up 150 making my way around, I'm going to take 180 minus 150. That's equal to 30 degrees. Our related acute angle in this case is 30 degrees. Let's continue it to the second one. So negative 110. So remember, with negative means we're going in the opposite direction. In this case, we're going clockwise. So that'd be negative 90. This would be negative 180. That's too much. So it's got to be in this quadrant here, quadrant 3. Our alpha value, our related acute angle, is that angle that's created between the terminal arm, the red one, and the x-axis. So let's calculate that value. Well, if this is negative 110, and I know the x-axis is 180, well, what's the difference between 180 and 110? Alpha is equal to negative 180 minus negative 110, is equal to negative 70. So why is it negative 70? So we're just calculating what's missing going up in that direction. But the related acute angle is always going to be the absolute value of that, 70 degrees. So related acute angle is 70 degrees in that quadrant there. Related acute angle is always going to be positive. Next one, 73. Draw our grid. Whoops, wrong color. This one here, so if we're starting with our arm along the x-axis in the same spot, that's our principal arm, and I go counterclockwise because it's a positive 73 degrees. Well, as I go up here, we get to 90. That's too much. So it must be in the first quadrant, somewhere around here. So in this case, the principal angle of 73 is the same as the related acute angle because the related acute angle is an angle that's created between the terminal arm and the x-axis. So in quadrant 1, principal angle is the same, 73 degrees. And we'll do our last one over here, same idea. Now this one's a coterminal arm. So in this case, we're going in the counterclockwise direction because it's positive 470. So I will have 90, 180, add another 90, 270, add another 180, we're at 360, add another 180, we're at 450. And so if I'm at 450 to get here, I know that it's just a little bit more to get to 470, so I know it's in the second quadrant. Our related acute angle is the angle that's created here. So I got to figure that out. Well, our x-axis is 180 degrees, but I need to subtract 470 minus that first circle because I want to take out this first circle here. I'm just interested in what happens after that first circle because it's a coterminal angle. So I'm going to take away 360. That's our alpha. That's our related acute angle. So 180 minus, we're subtracting the first circle. So that's 110 degrees. So what does that mean? That means that our angle, terminal arm, continued another 110 degrees after it passed the starting spot. So all I'm doing is finding the difference between 180 and 110, and we get a related acute angle in this case of 70 degrees. Like so. So let's continue along. We'll look at radians and what they are. So remember, let me just change the color. Back in grade 10, we used degrees to measure angles. In grade 11, we started to learn about radians. So what is a radian? Basically, we think of it in terms of a circle, something going around that terminal arm. If I imagine that I create an angle in here, I'll use a different color, and our angle is theta. One thing that we do know about this circle is that it has a radius. That would be the distance here and here. Might be the same. And one other thing that's created when we're dealing with a circle is this distance around the outside. This is called the arc length. So you can imagine as I'm making that angle bigger, the arc length will get bigger. So let's continue. Let's take that same idea and I'm going to erase. So we'll erase those and we'll create a bigger angle. So what happens if I have my angle up here? Now in this case, you'll notice that the angle has increased between the two lines of the radius. And when that angle increases, what also increased is the arc length as well. So as that angle increases, the arc length also increases. We call that A. So there's a relationship that happens there. So what the radian is, it's just a measurement that takes the arc angle and divides it by the radius. That's all we're dealing with. So let's have a look at that. So it says, notice that as the principal angle, theta, increases, the arc length carved out on the circle also increases. When the length of the arch is exactly the same as the length of the circle's radius, the measure is 1 radian. So here's an example of 1 radian. So the angle that we've created has carved out a distance that is exactly the same as our radius, in this case r and r. So that would be an example of 1 radian. Keep going along here. Now in this case, the angle that's been created has carved out a length of 2r. So that would be called 2 radians. And same over here, you can see that the angle that's created has carved out an arc length equal to 1, 2, 3r. That's considered 3 radians. So, and that's written down below. The number of radians that we have is equal to the arc length divided by the radius, or more simply, theta is equal to a over r, where theta is the measurement of the angle in radians. So, one thing that you're going to find out as you're working through this book is that when you're working with radians, the unit RAD, usually not there. Up above I put it, but usually not going to be there. You're just going to see an angle of 7. So you're going to assume that 7 is in radians, or an angle of 2. That means 2 radians. Otherwise, you'd see 2 degrees, for example. So find the indicated quantity. So this case here, we're talking about 2 radians. We have a radius of 5. So in this case, I know my angle is 2. I know my radius in this case is 5. And we had a formula. The formula was theta was equal to a over r. So in this case, we know 2, 1 unknown. So I'm going to plug these values in. 2 is equal to a over 5. And as I multiply both sides by 5, we're going to get 10 is equal to a. So what does that mean? That means that the distance that we have around here is equal to 10. So if it was 5 centimeters for the radius, well, 10 centimeters has been carved out along the outside of our circle there. And that makes sense because we're dealing with 2 radians. So that means that it should be the distance of 2 radiuses. Radius was 5, so 2 radiuses is 10, carved out along the outside. So let's keep going. Next one that we have here, I have a bigger angle. And the arc length that we're dealing with, in this case, 40. So let's fill those in. Angle, I don't know. Arc length, I know is 40. Radius in this case is equal to 12. So that's enough for us to solve it because we know the formula. Theta is equal to a over r. So theta is equal to a, which is 40, divided by 12. Theta is equal to, put in our calculator, 40 divided by 12, and we end up with 3 1/3. Or 3.333. That continues on forever. And the last one over here, notice that the radian is written a little bit different. So what does that mean? Well, I know that my arc length is equal to 25. I don't know my radius, but we know that our angle is equal to 7 pi over 6. So let's fill those in. Angle is equal to 7 pi over 6. My arc length in this case is equal to 25, and we're trying to find out our radius. So I'm just going to fill these into our formula. theta is equal to 7 pi over 6 is equal to 25 over r. So if I'm trying to solve this, we can cross multiply and divide. So if I cross multiply 25 times 6, we get 150. If I multiply 7 pi times r, well, I'm going to get 7 pi r, and then divide both sides by 7 pi. We get r is equal to, remember pi is 3.14, but 150 divided by 7, and we get about 6.8. So that means that the radius in this case is 6.8. So let's continue along here. So how do I convert between the two? Because we know in grade 10 we learned about degrees. I know in grade 11 we learned about radians. How do we work with them? Well, I need a relationship between the two. So this one says, for any circle with a radius of r, their circumference is 2 pi r. And we know that. So in radian measures, the angle created by one full circle, 360 degrees, is theta is equal to the arc length, the full distance around, divided by radius. So if radius is equal to r, we fill that in. So one full circle is 2 pi r. That's just the formula for circumference. If radius, we called that r, well, what's going to happen is both those are going to cancel out. So the distance around one full circle is 2 pi. Makes sense. So since we know one full revolution is 360 degrees, well, I know that 2 pi is equal to 360 degrees. And if I divide both those by 2, I'm left with this relationship here. Pi radians is equal to 180 degrees. We're going to use that relationship to find out our calculations to convert from one to the other. Because if I know this, well, I can divide both sides by pi, or I can divide both sides by 180 in order to get 1 radian, or I can get 1 degree. So I can get my multiplier by that. So the above relationship will allow us to convert any of them, radians or degrees, and vice versa. So essentially, convert from degrees to radians, multiply by pi over 180. To convert from radians to degrees, multiply by 180 over pi. So that's going to be our relationship that we're going to be using. So let's try that. So take each radian measure and to convert it to degrees. So we're going to be using this formula here. I'm going to take each of these and multiply by 180 over pi. So here, if I multiply by 180 over pi, so I'm trying to convert pi over 3 into degrees. Well, if I do this, I know that the pi's cancel out. I'm left with just 180 over 3, and when I divide them, I get 60 degrees. Like so. Continue with the next one. I know I'm going to be multiplying by 180 over pi. So in this case, we're going to have to put it into our calculator, 2.2 times 180, and then divide it by pi, which is 3.14. Divided by pi, and we get 126 degrees. And most of it's just the calculator work. Next one, same idea, multiplied by 180 over pi. Well, I have a pi on top and bottom. They're going to cancel out. That leaves me with just negative 3 times 180. I get negative 540. Remember, the negative just tells us what direction we're going. And that makes sense because negative 540 is more than one full circle around. And same with negative 3 pi. That's 2 pi is one full circle around. So 3 pi would be more than one circle around. And lastly, 1 radian multiplied by 180 over pi. We get 57. So 1 radian is equal to 57.3 degrees. Those are all degrees, the answers. For the next one, find the radians from the following degrees. So we're just going to multiply by its opposite. So I'm going to multiply by pi over 180. So I can either put that into my calculator and get a decimal for it, or I can try to reduce the fractions that we get, because if we do this, 45 times pi, right? So like 45 over 1, 45 pi over 180, which just gives me pi over 4. That would be the radian measure for that. You can put in pi divided by 4. of 0.78. I don't put degree or anything like that because it's in radians. You could put RAD if you want. Next one, 510, same idea. I'm going to multiply by pi over 180. That gives me 510 pi over 180. And then we can try to reduce that fraction. I know that 30 goes into both those numbers evenly, which would make that into 17 pi over 6. Or if I wanted to get that as a decimal, I can take 17 pi and divide it by 6, and we'll get 8.9. And same for the last one, multiplied by pi over 180. Now in this case, I'll have negative 210 pi over 180. 30 goes into both those numbers evenly. 30 goes into negative 210, negative 7 times. And 30 goes into 180 6 times. Or I can get them in terms of a decimal if we wanted as well. By same idea, putting it into our calculator, negative 7 pi divided by 6. Here we get negative 3.67, around it. And that's in terms of radians. Now, normally you're going to see it either as a fraction, the pi sign in it, or you may see it as a decimal. Both are okay. So now let's use this idea. All right, so in the word problems, we deal with what's called angular velocity. And the way that we show that is with this kind of cursive W. And it calculates the speed that something is spinning in a circle. So angular velocity takes into account radians per second. Oops. So let's have a look at an example here. So what we're going to do is imagine that we have a fan in our classroom. So I'll draw a fan here. Beautiful. And what we want to take into account is its angular velocity. I want to know how fast is that fan at the front of the room spinning in radians per second. So this W is equal to the amount of radians for every second. We know that our fan is rotating 450 revolutions every minute. So I need to take that 450 revolutions and convert that into radians. And minutes, I need to convert those into seconds because the question says per second. So one thing that I do know is I'm going to have 60 on the bottom because in 1 minute there's 60 seconds. On top, I'm going to have to calculate the amount of radians that are in 450 revolutions. Now, what revolution means is one full circle. So if you imagine this fan over here, so imagine I have a spot here. One revolution would be the amount for one full circle like that. So I do know that one revolution has 2 pi radians. So I want to know what it's going to be for not just one revolution, but 450 of those. Oops. So when I multiply those ones together, I'm going to get 900 pi. So that means there's 900 pi in terms of the angle, right? 2 pi, 4 pi, 6 pi, all the way around. 450 times all the way up to 900 pi. So that's the amount of radians. 900 pi radians. Now what I want to do is divide those because I want to know what it is per second. So 900 pi divided by 60 is 15 pi radians per second. 15 pi radians per second. So I know that 2 is 1 revolution. So we're going around a few times, really 7.5 times every second. So if the radius of each blade is 10 centimeters long. So what does that mean? Well, here's our fan. I know the distance from the center to the outside is 10 centimeters. I want to know how far has the end of each blade traveled after 6 seconds. So I'm going to draw another picture here. So let's suppose there's like a little piece of tape on the end of one blade, and I want to know after 6 seconds how far has that piece of tape on the end of the blade traveled. So what do I know about that? Well, that's the arc length that it's gone. One formula that we talked about before was the radians are equal to the arc length divided by the radius. Well, we know the radius in this case is 10 because it says each blade length is 10. So that's going to be our denominator. I'm going to change the color here. I know that we're going to have 10 on the bottom. The arc length is what we're trying to calculate because that's the amount of distance that piece of tape or whatever it is on the end of the blade has traveled. So what I need to do is find out the amount of radians that our blade traveled in 6 seconds. So I know the speed of the blade is going at 15 pi radians per second. So if I multiply that by 6, because I want to know what it's going in 6 seconds, I know it's going 90 pi radians in 6 seconds. So I can put that into the formula because that was our unknown over on the right. So let's put that in the formula and we'll solve for that arc length. So our radians was 90 pi is equal to A over 10. And if I multiply both sides by 10, I know that the arc length that the blade has traveled is 900 pi. So what does 900 pi mean? Well, I can put that into my calculator. When I put in 900 pi, I get A is equal to 2827.4. And in this case, it gave us the centimeters as the measurement for the blade. So that many centimeters our blade has traveled in 6 seconds. So let's try a second one, kind of similar to it. This one says the London Eye Ferris wheel. So there's a Ferris wheel in London. It's called the London Eye, very big one. And it says it has a diameter. That's the distance from the top to the bottom. So if I was to draw this Ferris wheel, it tells me that the distance from the top to the bottom is 135 meters. It says it completes one full revolution in 30 minutes. So it goes 2 pi in terms of radians in 30 minutes, if we think of it that way. We want to know what is the angular velocity. So same idea as before. Angular velocity is equal to radians per second. So let's take what we know. We don't really have to use much information in here other than I know that it completes one revolution in 30 minutes. So one revolution is 2 pi radians. Talked about that before. It's one full circle. And 30 minutes. Well, 30 times 60 to convert it would be 1,800 seconds. And if I divide that, that's pi over 900. So that's how fast we're going. Pi over 900 radians a second. So we got the speed. Now, how far would a rider have traveled in 10 minutes on the ride? So let's imagine, here's me. I got on the ride. I was so happy. I traveled around. I know that it takes 30 minutes for one full revolution, so I traveled all the way to maybe about here. And I wonder, what distance did I travel? That's the arc length that we went around the outside. So keep in mind our formula that we know before. Our radians is equal to the arc length. That's what I want to know. How far did I travel around the outside? Divided by the radius. So what I'm going to have to do is I'm going to have to find out what is the angle that this London Eye travels in 10 minutes. I know the radius because the radius is half of the diameter, so 135 divided by 2. That's going to be my radius. I'm just going to plug in all that information. I'm looking for the arc length, the amount of time, the amount of distance that I traveled around the outside. So let's take our theta. Let's figure out what that is. So I know that in 1 second, we travel pi over 900. But I'm interested in 10 minutes. So in 10 minutes, there are 10 times 60 seconds. So when I put that in my calculator, I get 2 pi over 3 radians. That's our angle that we're dealing with. That's our theta that we're working with. So that's going to be the value that I plug in for theta. We know our radius. Well, that's 135 divided by 2, which is 67.5. So maybe I can put that here. Our radius is equal to 135 divided by 2, which is 67.5. And we're just going to plug that into our formula. So we use different colors to keep it organized here. Our theta is equal to A over R. So we have 2 pi over 3. You could add a decimal for that if you want to. Doesn't matter. Is equal to A over the radius, in this case 67.5. When I cross multiply, I'm going to get 3A is equal to 135 pi. 141, and the units that we're using is meters. I could use decimal point 4 meters, and that's the amount of distance that I traveled riding this ride and had a great time in the first 10 minutes to travel 141 meters. And that's this first part. We'll talk to you soon.